Let's let our x sub k have a numerator of a sub k and a denominator of b sub k, where these two are relatively prime, so our fraction is in lowest terms. Our first term in this sequence is 25 over 11, that's x1. Let's calculate x2. We're going to take 1/3 of 25 over 11, add its reciprocal, and subtract 1. Here inside the parentheses, our numerator is 471, so 3 divides evenly into it. So in this case, when we reduce our fraction, we have that this numerator is a multiple of 3. Let's see if this happens for all of the terms in our sequence. So is the numerator, before we divide by 3, is that a multiple of 3? Our first term, again, is 25 over 11. So our reduced numerator, a1, is 25. That's 1 in mod 3. And our denominator is 11, which is 2 in mod 3. Here is our formula for x2 in terms of a1 and b1, and we'll find a common denominator inside the parentheses. This last product suggests that we can write this as the square of a binomial. So we'll add and subtract minus a1 b1 and write this as the square of a1 minus b1. So let's take this numerator before we reduce it and substitute in our mod 3 residuals for a1 and b1. Inside these parentheses we have 1 minus 2 plus the product of 1 and 2. So our numerator again is divisible by 3. Let's see what the mod 3 residual is for the reduced numerator. This is after we divide by 3. To do that, we can take our original numerator before we reduce it and find the mod 9 residual of this expression. So let's find the mod 9 residual of a1 and b1. a1 was 25, and that's 2 less than 27. b1 is 11, which is 2 more than 9. And we'll plug these in. Inside the parentheses, we have minus 2 squared plus the product of these. This is 16 minus 4, or 12, which is 3 in mod 9. This means our numerator can be written algebraically as 3 more than a multiple of 9. Our reduced numerator will be 1/3 of this expression, and we'll substitute 9k plus 3. This is 3k plus 1. This means our second reduced numerator is 1 in mod 3. Recall this was the same as a1. Let's find b2 in mod 3. The denominator was just the product of a1 and b1. In mod 3, that was 1 times 2, or 2 in mod 3. This is the same thing as b1. So by induction, all of our reduced numerators are going to be 1 in mod 3, and all of our denominators are going to be 2. Returning to the problem statement, we want to find the 2025th term in this sequence, written as a fraction in reduced terms, m over n. This is going to be in the numerator a sub 2025, and then the denominator b sub 2025. We're asked to find the sum of m plus n, which is going to be the sum of a and b for 2025. We'll simplify this a bit by letting z for the kth term be the sum of the numerator and denominator for that term. Let's plug in our values for the reduced numerator and denominator. The original numerator will be divided by 3, and this is our expression, and we'll add the denominator to that. We'll expand this binomial, keep this the same, and we'll take this last term and multiply it by 3 and stick it inside these parentheses. We have 4 times the product of the a and b here, and then minus 2. So that leaves us with positive 2. And this is the square of the binomial a sub k minus 1 plus b sub k minus 1. And recall that z is equal to a plus b, so we'll substitute that here. And this is our expression for z sub k in terms of the previous z. And we want to find z sub 2025. So we'll take this step by step. I'll replace z sub k minus 1 with 1/3 of the square of z sub k minus 2. Let's do this a couple more times so we can find the pattern. Now we'll replace z sub k minus 2 with 1/3 z sub k minus 3. This is squared, and then this is, and then this is, and we'll do one more. Now we'll replace this with 1/3 z sub k minus 4 squared, and squared. Our terms are going to have powers of 3 multiplied by powers of z. So let's generalize these powers for any z before z sub k. Let's take a look at what happens when a is equal to 3. That's this expression over here. The power of 1/3, we're going to get 1 from this first one. We're going to get the square of 1/3 from here. And we're going to get 1/3 to the 4th power from this innermost 1/3. And now we'll find the power of z to the k minus 3. We square it 3 times. so that's z to the 8th. Altogether, we're multiplying 7 of these 1/3 and 8 of these z's. In terms of 3, our value of a, this is going to be 1 less than the 3rd power of 2, so 2 to the 3rd minus 1 up here, and this is z to the power of 2 cubed. We'll try this one more time where a is equal to 4. So we've got a 3rd here, we have a 3rd squared, and a 3rd to the 4th, and a 3rd to the 8th. Here we have z to the k minus 4, and that's raised to the 16th power. Altogether, we have 15 1/3. When these exponents are written in terms of a equals 4, this is 2 to the 4th power minus 1, and 16 is 2 to the 4th power. Now we can generalize. For any a, z sub k is going to be 1/3 to the power of 2 to the a minus 1. For z sub k minus a, the power is 2 to the a. We'd like to express z sub 2025 in terms of our first fraction, z sub 1. This was the sum of our numerator and denominator, 36. Since we want this expression to be in terms of our first term, z1, let's let k minus a be equal to 1, so k is a plus 1. And we'll substitute here, and we'll substitute our value for z1. This is going to be 36 to the power of 2 to the a. Let's cancel out some of these 3's. In our denominator, we have 3 to the 2 to the a minus 1. 36 is 3 times 12, so this is 3 to the 2 to the a and 12 to the 2 to the a. All of our 3's are going to cancel except for 1, so we're just left with this. And our problem asks for z sub 2025, so we'll make that substitution. This is 12 raised to the power of 2 to the 2024. And in the problem statement, we want the mod 1000 residual of this number, so we'll do that. First by noting that 1000 is 8 times 125, so we'll find the mod 8 and the mod 125 residuals separately. First for 8, 12 is 4 times 3. We have enough 2's in this prime factorization so that this number is going to be a multiple of 8. And now we'll do mod 125. The second factor is the trickiest, so we'll start with this. A key Aime formula is Euler's theorem. You should know this. It has that a number raised to the phi of n is going to be 1 in mod n. This is true if a and n have no factors in common. Phi of n is the number of numbers less than or equal to n that are relatively prime to n. Checking in this example, we have that the GCD of 12 and 125 is 1, so we can use this formula. Here our mod is 125, so 12 to the power of phi of 125 is going to be 1 in mod 125. Numbers that are relatively prime to 125 do not have 5 in their prime factorization. That's 1/5 of those numbers. So there are 100 of them. So we know that 12 to the power of 100 is 1 in mod 125. Ultimately, we want 12 to the power of 2 to the power of 2024. So we're going to break this up into powers of 12 to the 100, since we know that's 1. And then we're going to have our leftover exponent. That will be the residual in mod 100. So we're going to try to find e, this remaining exponent, when we divide by 100. We'll use Euler's theorem again, noting that 100 is 4 times 25, and taking these mods separately. 2 to the 24 is clearly a multiple of 4. So now we'll find 2 to the 2024 in mod 25. Using Euler's theorem, we know that 2 to the phi of 25 is 1. So we'll calculate phi of 25, numbers that are relatively prime to 25. There's going to be 1/5 of those numbers that share a factor of 5, so we'll subtract those out, leaving us with 20 numbers that are relatively prime to 25. So we know that 2 to the 20th power is 1 in mod 25. We want to figure out what 2 to the 2024 is, so we'll express this in terms of 2 to the 20th. We're going to have 101 of these, and then 4 more 2's. So in mod 125, these are all 1, and this is 16. Let's go back to mod 100. We can rewrite this algebraically as 16 more than a multiple of 25, and we need this to be 0 in mod 4 as well. This is a multiple of 4, so we can discard it. This gives us p is 0, which means it's a multiple of 4, and we'll plug this back in for this first expression. So 2 to the 2024 is 16 more than a multiple of 100, so that's 16 in mod 100. Recall that we were doing this because we were taking 12 to the power of 2 to the power of 2024, breaking these up into 12 to the power of 100. All these factors are equivalent to 1. Pulling out all of these hundreds, that's this mod 100, leaves us with 16 more 12s. And this was our expression in mod 125. And we also had that 12 to this power was 0 in mod 8. Let's see if we can reduce this large number. We can write this as 12 squared raised to the 8th power, because 144 is close to 125. It's 19 more than 125, and we'll do it again. We can write this as 19 squared raised to the 4th power. That's 361. Let's subtract 125. That's still a big number. Let's subtract 125 again. That's probably the best we can do in mod 125. So we'll write this as negative 14 squared and then squared again. That's 196 squared. Subtracting 125, we're down to 71 squared. And if we do it once more, we get minus 54, which is a little smaller. Squaring this, we get 2916. And pulling out multiples of 125, we're left with 41 in mod 125. So our z value for 2025th term will be equivalent to 3 times 12 to the 16, and we'll replace this with a 41 or 123 in mod 125. This is just 2 less than that. And we also had that z 2025 was 0 in mod 8. So we'll go back to mod 1000. This is 2 less than a multiple of 125, and we need this to be a multiple of 8. A quick guess and check gives us p is equal to 2 is a solution. So writing this algebraically, this is 2 more than a multiple of 8, and we'll substitute it back up here. This is 125 times p, which is 8q plus 2, and then we'll subtract 2 again. Here we get our 1000 times q. This is 250 minus 2. This was the sum of a and b, which was our reduced form of our fraction, m and n, and this is 248 in mod 1000. If you'd like me to solve any other math contest problems, please leave them in the comments.